This is part 2 of my introduction to acids and bases. In the previous video, we went over what acids and bases are and what their properties are, their molecular formulas, how to name them, how they're formed. We got a little bit into water dissociation, which we will now continue. You may recall that in the previous video, we animated the collision of two water molecules to show how water can self-ionize. It doesn't ionize very much, but this gives us a hydrated hydrogen ion and hydrated hydroxide ions. This establishes an equilibrium. Most of the water molecules remain as water, but some have broken up, as you see here, into hydrogen ions and hydroxide ions. This is an equilibrium. Water is breaking up into ions at the same time and at the same speed that the ions are running into each other and reforming the water. There is an equilibrium constant for this process, but first we need to find the concentration of the hydrogen ions and hydroxide ions. And for pure water at 25 degrees Celsius, the hydrogen ion and hydroxide ion concentrations are equal, and it's 10 to the negative 7th molar. That changes a bit with temperature. The equilibrium expression, and this is something you study in equilibrium, is the product of products, the hydrogen ion and hydroxide, divided by the product of reactants, and only water is the reactant. That's why we have written it this way. But the concentration of water doesn't really change, does it? So what we do is we treat the concentration of water as a constant, and we just plug a 1 in there, and what ends up then is that the equilibrium constant is just the hydrogen ion times the hydroxide concentration. That's 10 to the negative 7th molar times 10 to the negative 7th molar, which is 10 to the negative 14th molar squared. But since that's really a hard thing to get your mind or mouth around, we just usually ignore the units on these equilibrium constants. So we just say the equilibrium constant is 10 to the negative 14th. Now, it's time to define pH. pH is the negative logarithm of the hydrogen ion concentration. This is the definition, the negative base 10 logarithm of the hydrogen ion concentration. That means that if we raise 10 to the negative pH, we get the concentration of the hydrogen ion. We'll work with that quite a bit when we use acids and bases. For pure water, that is, there's nothing dissolved in it, the hydrogen ion concentration is 10 to the negative 7th. And remember, logarithm is an exponent, so what we're really asking for is the negative value of the exponent on 10. Oh, well, the negative value of the exponent on 10 to the negative 7th is 7. Now, we would naturally believe that if we define the pOH, it is the negative log of the hydroxide ion concentration, and so it is. Therefore, the pOH of pure water is the negative log of 10 to the negative 7th. It is also 7. Now, as the hydrogen ion concentration increases, the hydroxide ion concentration will decrease because they have to multiply to give 10 to the negative 14th. And therefore, as the pH decreases, the pOH increases. Counterintuitively, although pH measures acidity, as the pH increases, the solution becomes less acidic and more basic because we're working with 10 to the negative pH. A solution that is 1 molar HCl, and HCl is a strong acid, breaks up 100% into ions. It must be 1 molar hydrogen ion concentration. What that means is that none of the hydrochloric acid remains as an HCl molecule in the water. all of it is broken up into hydrogen ions and chloride ions. But the pH is equal to the negative log of the hydrogen ion concentration, which is the negative log of 10 to the 0, and therefore the pH is 0.0. Another problem. What is the pH of 0.10 molar hydrochloric acid? Remember, it's a strong acid, breaks up 100%. Definition of strong acid tells us then that the hydrogen ion concentration must be equal to the initial hydrochloric acid concentration. Therefore, the pH being the negative log of the hydrogen ion concentration, the pH is the negative log of 0.10 molar, and that's 1.0. Likewise, the pH of a 0.010 molar hydrochloric acid solution is 2, of the 0.0010 molar strong acid is 3, and so on, as you get closer to 7. Dr. Hubert Alyea gave us a very fine diagram, and this is a logarithmic scale for those of you who are purist mathematicians. And I always suggest that students just draw this every time they see an acid-base problem, because it's kind of like a map of acids and bases. As you can see, the hydrogen ion concentration is largest on the left, and I've drawn it in red because hydrogen ions are usually shown in red. The hydroxide ion concentration is largest on the right. As you recall from what you just learned, when you get a pH of 0, the hydrogen ion concentration is extremely high, and so we've got this big gap. When the pH is 14, the PaOH is 0, because we have to add them together, we get 14. And so the hydroxide ion concentration is very large when the pH is very high. As the hydrogen ion concentration goes down, the hydroxide ion concentration goes up. We know that also is true. And we've also drawn the POH on top, starting on the right at 0, where the concentration of the hydroxide would be such that the exponent would be 0. That would be 1 molar. And over here on the left, where we have a very high hydrogen ion concentration, the POH would be 14, and the hydroxide ion concentration would be very, very low.